are no
they have
eyes.
eyes.
There are no examples in this one.
What type of store do apes own?
MS. I said the word MS.
A monthly business.
How does the sun
Something
relate
related.
hide and seek?
All right, 311 is about spectroscopy and the electromagnetic spectrum, which we discussed the electromagnetic spectrum in Chemistry 1. So a lot of this stuff is review from what we have talked about before. Remember that energy can travel through space by electromagnetic radiation. So the radiation could be like ultraviolet rays from the sun. It could be microwaves, goodness, X-rays, radiation from heat, that would be infrared kind of radiation. So we have three primary characteristics of waves: wavelength, frequency, and speed. Remember that wavelength is symbolized by the upside down Y, which is called a lambda. It's the distance between two consecutive peaks or troughs in a wave. The frequency is the Greek letter nu, which is a V. It's defined as the number of waves or cycles per second that pass through a given point in space. All types of electromagnetic radiation, also known as EMR, travel at the speed of light. So that means that a short wavelength will have a high frequency, and a long wavelength will have a low frequency. This inverse relationship between wavelength and frequency is shown by the speed of light equation, where the wavelength is in meters. So maybe make a note to yourself or underline these. Frequency is in cycles per second or hertz. And then c is the speed of light, which in Chemistry 1, we just use 3.0 times 10 to the 8th. On your equation sheet for the exam, it uses a more exact number. So I don't think when you solve, if you just use 3.0, that it would be very, very different than if you use the 2.9979, but that one is the one that is on your equation sheet, okay? The SI system, it's understood that 1 cycle per second is equal to 1 hertz. So that's why you might see it in either fashion. And when you label frequency, either one is okay. We can classify electromagnetic radiation from our spectrum. This is not in color in your notes, unfortunately, but it, hopefully you know visible means the rainbow of colors, and you know the order in which the wavelengths go. Maybe make a little note to yourself, especially if you might not be able to see all the colors of the rainbow, that this side is the violet side. The side closer to the ultraviolet is the violet side. And then the closer to the infrared side is the red wavelength. You never noticed that before. And so just from these numbers, remember when you have a rainbow, and we color a rainbow like in kindergarten, what color do we usually put on top of the rainbow?
Red.
Red. And which color usually goes on the bottom? Purple. And the reason why it's curved is because for the same distance, the red light has a longer wavelength, so it has to cover more distance than violet does. So that's why red goes on top, because it's a bigger curve than the purple or violet on the bottom. Fun stuff. The nature of matter has been studied since the 19th century. We believe that we solved all problems related to matter and energy, but in 1900, Max Planck, or Planck, found experimental results that suggested differently. He saw that when heated to incandescence, the radiation profiles could not be explained by the physics of his day. So like, this is a pickle that you have electricity going through it, and that is what incandescence means. So have you guys ever heard of like an incandescent light bulb?
Yeah.
We don't have those light bulbs as much anymore because we have fluorescent light bulbs now, or like LED bulbs. But incandescent, they had a tungsten wire that would be heated from the electricity running through it, and it would glow, which would produce light. Yeah.
I've seen that before,
The pickle being lit up. Just because it has electrolytes in there. Yeah.
I thought it was fake.
I've never actually done it myself, but yeah, you could do it. You could. You could
Charge
do it.
your phone with a nickel?
I don't know if you could charge your phone with the bulb.
But they did something to it, and they put their phone charger in it, and
And they were able see that it was creating electric current. That's cool. Planck could account for these observations only by postulating that energy could be gained or lost with whole number multiples of the quantity hv, where h is constant, which in Chem 1 we said that it's 6.63 times 10 to the negative 34, sorry, but on your equation sheet it's 6.626. So the energy, what do you think the unit for energy is going to be? Joules. And then the frequency is the same, hertz and or cycles per second, either one. Okay? So Planck's result was a surprise because it seemed clear that energy is in fact quantized and only can occur in discrete units of size h times v. So these packets, the values that were achieved by taking the frequency times the constant, are called quanta. So this system can transfer energy only in whole quanta. So this suggests that instead of being wave-like, energy travels and light travels as a particle instead. Remember, what did we learn about in Chem 1? Is it a wave or is it a particle? It is both. That's what 312 is about. Some differences in absorption or emission of photons is related to the different types of molecular motion. So there are 3 different types of molecular motion. This is all the new stuff from the book that we don't really have questions over because there's not in the book. It's in the Apex section. Ultraviolet and visible radiation is associated with electronic energy levels. So we'll talk about that in a second. Infrared radiation is associated with transitions in molecular vibrational levels. So ultraviolet is more like how do the electrons move, and then infrared is more how is the molecule as a whole vibrating, how fast is it vibrating, and then microwave radiation is associated with transitions in molecular rotational levels. So how is it spinning? Is it spinning clockwise, counterclockwise? In what direction is that rotation? So spectroscopy is the study of the interaction of electromagnetic radiation with matter. It provides a non-destructive and highly sensitive method for obtaining information about the identity, structure, and properties of substances. The lab that we're going to do after this Unit 3 test, we are going to use a spectrophotometer to actually measure the concentration of solutions. So we will know what the solution is, and we know sometimes that when you change those concentrations, the colors can be more vibrant or less vibrant. So that's what we're going to measure, and that's, I think, 313. That we'll talk about that more. So, the electronic spectrum of a molecule, which typically occurs in the UV or visible regions, provides information about the spacings of electronic energy levels in the molecule. So this helps us to determine the electronic structure of a molecule. We have seen this before already this year. Does anybody remember? Starts with a P. Photoelectronic spectroscopy, PES. You guys had graphs like this, remember? And we had to like label it 1s2, 2s2, like that, and you figured out the element. That is a type of spectroscopy that we have already talked about this year. So this usually, we're gonna like see this more with visible light when you see that coming across. But it helps us to see more about the molecule. So when it's in the UV region, it corresponds to the energies of photons in the UV region. So when white light, just a reminder, consists of all the colors of the rainbow mixed together. So when a particular colors are absorbed, then the substance appears colored. So this is just a little physics review for you. The color that results is the sum of the colors that remain unabsorbed. So all the colors of the rainbow make white. What happens when it's black? What does that mean? It's lacking color. There are no colors if it is black. But like we see the sky as blue, so does that mean that blue is absorbed or is blue released? Blue is released. And so maybe there's some other visible wavelengths as well, but the combination, when they all add up together, they make it appear to our eyes as a blue color.
So you're saying the ocean reflected on
This is a graph that also shows the amount of light absorbed. So the word carotenoid. Does anybody want to take a guess of that? What contains that?
Carrot.
What did you say? Carrots and oranges. Yeah, it's because if you look at the color, it is orange. But do you see how the peak is over like the blue area? If you've ever seen a color wheel, like green is opposite red, blue is opposite orange, purple is opposite yellow, kind of thing. I might have to show you that sometime. So that kind of tells you if the blue wavelengths of light are all being absorbed, what's left over, what's being remitted out to you to see with your eyes, is then going to form some sort of blue color because it's the opposite of the color wheel. There's also like chlorophyll on here, and there's different peaks for the chlorophyll. The carotenoid only has one peak, but it's just a different way to see some of the stuff that we talked a little bit about in Chem 1. Okay, the next type of spectroscopy is vibrational. So this corresponds to the infrared region, the IR region of the spectrum. A particular bonded pair of atoms has a characteristic vibrational frequency that is relatively insensitive to its molecular environment. So it's going to vibrate no matter what. If you've ever used like night vision goggles or a scope, it's using the vibrations that come from this IR region of the spectrum to give you that picture through the scope. A signal that appears in the IR spectrum at a characteristic frequency provides good evidence that this particular atom is present within the molecule. So these pictures are on the next page. I included them in your notes. They're on the next page. But so when I say vibration, sometimes we just think vibrating just means like moving back and forth. But that's not always the case. There's all kinds of vibrations. You could stretch them, like pull them out and pull them back together. You could have one side stretching, not the other side. You could have them, so this is a water molecule, right? With the two H's. Maybe they're vibrating together, or maybe they're vibrating apart, sort of thing. Or maybe they're moving forward and backwards, kind of thing. And so then there's also the carbon dioxide pictures there to try and visualize that for you. So when I do vibrate in Chem 1, I usually just say like vibrate in place and I just shake my hand. But there are lots of different ways for these vibration moves to happen. Okay, so they're called normal modes when we have these vibrational motions, and there's all these different kinds of modes for that. Sorry. Okay, the IR spectrum of a molecule can be a great aid in identifying which atom groupings or types of bonds are present in a molecule, and then can provide valuable information for identifying a specific molecule. And then last but not least, rotational spectroscopy tries to identify how is the molecule rotating. So I have a picture here of water, and is it rotating around which axis kind of thing? So is it spinning clockwise, counterclockwise, in a different way? But this corresponds to wavelength, to the microwave region of the EMR spectrum. This is how, when you put food in a microwave, it heats up. Because the microwaves will make the waters in your food vibrate, and so that vibration causes it to gain energy to heat up your food. Have you ever like tried to heat something up and it didn't really do well, but then you like put some water on it and then it heated up a lot faster? And that's because you're adding water molecules that are affected by the microwave radiation to make it vibrate more, to make it heat up more. So I think that is the end of this section, right?